Hi everybody, welcome to another video in Calculus 2. In this section, we will go over all the convergent tests that we have and where to choose a test to determine if a series is convergent or divergent. So there are 1, 2, 3, 4, 5, 6, 7, 8, and 9 tests in total. So some tests will work better than the others, and the problem is when do we use what, right? This is from my experience. Maybe this will help you to choose the correct test, right? So usually when the first thing I look at the problem, I will look at the divergent test, because if h of k does not go to 0, then that is divergence. Then we don't have to do anything. So the divergent test, usually the first thing I will look at. So I would just say in the strategies, the first one I look for is divergent test. If the limit of the terms not equal to 0, then that is divergence. That's the first thing I look at. Second, have to know this ranking. All of those tests are good, but we have to know this ranking. Right, I'm just going to write this ranking again. So we start with the ln is that, and less than ln we have a constant, and then we have power, exponential, factorial, and I think this is we call the tau function, right? B is the base, going to be bigger than 1, and every other are constant. So I should say for that P bigger than 0, and B is the base, bigger than 1. Because if B less than 1, it go to, like for example, if we have a base that is less than 1, like 0.5, then that will go down to, it does not go to infinity, right? So we have to have that, right? So this ranking, how does that help? Now, if we have the term that is bigger or faster to infinity on the top, the whole thing go to infinity. If we have the term that is bigger or faster to infinity at the bottom, that goes to 0, right? And we have that ranking. And then after this ranking, this will be very helpful if we can use this. Now, the problem, every time we see the problem like this or this, meaning that we have more than one of this, more than one term on the top or the bottom, that is the comparison test. So for quotient, with more than one term on the top or bottom, and usually a term is one of this, the combination of more than one of this. And for that, we use comparison tests. And I put comparison tests. So either direct comparison test or limit comparison test. And what do we compare to? Compare to P series, compare to geometric series. That usually we compare to. Right. Might run out of space here, but right. So you have more than one term like this. So comparison test, comparison test. Right. Next. If we only have one of these terms on top, one of these terms at the bottom, that's the ratio test. So ratio test, if we have one on the top, one at the bottom, in terms of the ranking, then we can use ratio test. Usually if we have those scenarios. Once again, probably not LN, but for those. Right. Now, out of all this, perhaps the most obvious one is the alternating series test. When we have this, then that is the alternating series test. Alternating series test for when we see this or that. And then the root test is, of course, where we have the whole thing raised to some power. And the integral test usually is the last option, because usually when we do the integral test, we actually have to integrate, and usually that my least favorite one. So, and then we use root test when we see something raised to the k power. So those are the things that we watch out for. The integral test certainly works, but like I said, it's going to be my last option when I have to use it. So all of this is just from experience. Once you do a bunch of problems, you will develop your own strategies. But that's what I got from when I studied calculus 2. That what I have. Right. So now we have, I think, 10 examples. Right. The first one, that right, more than one term on the top and bottom. That is the comparison test. Comparison test. For that one, alternating series test. That one, yeah. So just some of the idea to get going. Right. So this one, comparison test. So we're just going to ignore the one. That's what we compare to, right? Now, before we do anything, the first test we should check is the divergent test. What happens when k goes to infinity for the term? Look at the ranking here. K, that is the power function. Ln of k, that is the Ln. So the bigger term on the top divided by the smaller term at the bottom. The bigger term on top, the faster term goes to infinity on the top. So this goes to infinity as k goes to infinity. So that does not go to 0 by divergent test. That is divergence. Right? So now we're going to write all of that. Usually for something like this, it is a divergent comparison test. Usually we could use comparison test. And I could say limit comparison test. That is my preferred choice. Limit comparison test usually has more work than direct comparison test, but it is easy to use. Limit comparison test is easier to use than direct comparison test, because direct comparison test we kind of have to come up with a function that we compare to, and usually not always easiest, because we have more than one term at the bottom or the top. That is the sign when we're using limit comparison test. So more than one term, top or bottom, we use limit comparison test. Before all that, always have to check to see what happened at the limit. So certainly we can do that. And so we will compare to k over ln of k. So when we write like that, we can compare to the series where we take the higher term, just ln of k. So when there are more than one terms, the term that go faster to infinity will keep it. Everything that less, everything on the left of it we will ignore, because ln of k goes to infinity, the 1 stay as a constant. So in that case we take ln of k. I might write a field here, because 1 does not go to infinity, or we can even write like that. So 1 is negligible. Right, so in that case we will compare to this. Certainly will work, but on this problem we will not do that. We can also use divergent test, because that term, when we see something like this and ignore the terms, and we see if we have the term on the right, the faster term to infinity on the top, then we use divergent test because the limit goes to infinity. Right. So this is one way to do it. Another way to do this, we can also use divergent test, because on this problem we have a faster term on the top over the ln of k, because we have the ranking is ln of k is slower to infinity than k. So when we take the limit with the faster term on the top, it will be infinity. And if it is not equal to 0, it will be divergence. Right. So in this section I try to write down the reason why we use some certain tests, because actually the actual solution is quite simple. So we can use that and we can use that. So the actual solution, I'm going to write in black ink, and we say it. Limit of k over ln of k plus 1 . So we take the limit of that term is equal to the limit k over ln of k. Once again, because the ln of k is a lot faster than 1, so the 1 is negligible. So adding 1 doesn't change anything. Right, so this one is put infinity in infinity over infinity. So when we use the Hospital rule, derivative of k is 1, derivative of ln of k is 1 over k. Multiply reciprocal. Divide by 1 over k is multiplied by k. So we just flip it. And this limit equal to infinity. Right, since the limit of the k term goes to infinity, that is not equal to 0, so that's why this divergence. So since it's not equal to 0, the series divergent. Right. So actually the solution is only these two lines, but we can use the limit comparison test as well. Right. So that's the first one. Next we have this problem. So again, when we have more than one term, the top and the bottom, just ignore it. So we compare to this. Now compare to this, k over k squared is 1 over k, and that one equal to 0 when k go to 0. So that one divergent test doesn't work. Right. So once again, we can use limit comparison test. Because we have more than one term, top or bottom. That's the same reason as we had before. And we compare to this series. Right. So we remove the 2 because the 2 is a lot smaller than k squared. Right. Simplify this. So we can compare to this. Or if we want to, we bring out the 5 and we only compare to 1 over k. which this one we know this is a harmonic series or P series with P equal to 1. So this is divergence. P series P equal to 1. So that is divergence. So when we compare these two, we compare with the divergence. So this one is divergent. But we actually have to show the work. So my question is, so that certainly works here. So let's just write the solution. Solution using the limit comparison test. Right. First of all, for the given series, let that be h of k. Now, we will compare to this. We compare to any of this will work, but I'm going to just choose the one without a constant. When we compare to that, b of k is equal to 1 over k. Right. Of course, when we compare, when we set it is divergent, then this is divergent. We actually have to show this. We need to show that the limit of h of k over b of k as k goes to infinity. So we will do that. Now this is not a ratio test, so no absolute values here. Just use that. So 5k. Right. There's a one subtle thing that I forgot to mention. Right. Do that. Multiply reciprocal. So we have 5k squared over k squared plus 2. Highest term on the top, highest term at the bottom. Oh, that still forgot the limit. Equal to 5. So what does this mean? Of course we can look at this. By the way, what I forgot to mention is in limit comparison test or comparison test, the term have to be positive, which we do have here. Right. So what happens if we have that? Now remember, when we compare rates, when we divide by two things, and when we have a constant, a finite number between 0 and infinity, when this number is between 0 and infinity, a finite constant, that means they have compatible rate. That means behavior of a of k and b of k are the same. So since b of k is divergence, so is a of k. Right. So I will write that again. Since we have a constant here, and that is if it is between 5 and 0 and infinity. So because we have 5 is between 0 and infinity. That means a of k and b of k have comparable rates, comparable growth rates. And when we set that, I could use the sequence, I could use a function, but we just say a of k and b of k have compatible growth rate. All the sequence behave this, all the series behave the same. So when we have that, they have comparable growth rate, or we say AK and BK behave the same. I did not say the sum are equal. I said they behave the same, meaning both will converge or both will diverge. And since b of k is the harmonic series, diverges. A of k also diverges. Thus, a of k also diverges. So that's usually how the limit comparison test will go. If there are more than one term, just ignore everything. Keep the highest term, the one with the highest ranking, and then we do that. Now, and when we divide and we use the growth rate to determine, in this case they have comparable rate, the series will behave the same, and one convergent, the other one will convergent. But since one of them divergent, the other one will be divergence. Right. Now, if we have to look at this in terms of the limit, the divergent test, if we just find the limit, I don't have enough space here, but if we take the limit of that term, the limit equal to the highest term on the top, highest term on the bottom, this is just limit of 5 over k. So, and that is equal to 0, which means divergent test is inconclusive. So we cannot say if the series is convergent or divergent using the divergent test, because the k term go to 0. So if the k term not equal to 0, divergence, which we don't have here, we have the term go to 0, that means divergent test cannot be used. Right. Right, so in that case we use a limit comparison test. I write a little more than what we need to, but I said it's better to write more details here, so all the reason behind this. Right, next test, this. Now, this is obvious, right? Because every time we see the -1 raised to the k power, or -1 to the k plus 1 power, or k minus 1 power, or anything that has -1 raised to the power that alternating between even and odd, that is alternating series. So we don't have to do much. We know for sure this is alternating series. Right. The reason that this problem we have 2, just because if we have 1 in here, 1 square minus 1 is 0. So we start at 2, just so that the first term is not going to be 0. We don't want to divide by 0. Right. But as mentioned before, when we see something like this, that is automatically alternating series. And if it is alternating series, we will write there's, like I said, there will be more than one way to do this. I'm just going to write the obvious here, alternating series. So for alternating series, we write out the alternating -1 raised to power, and what's left is h of k. Right, I'm going to write alternating series test. We need to check two things. First, does that go to 0? Right, so we take the limit h of k and we have 1 over k squared minus 1. Right, k squared or minus 1 or just 1 over k squared. Again, the minus 1 here is negligible. So finite over infinity, we did this many times. So this is equal to 0 because finite divided by infinity. So that is because it's equal to 0. A finite number divided by something approaching to infinity, that equal to 0. So that check. The second one we check is h of k non-decreasing, non-increasing. There's two ways to do this. Either we take derivative or we just use some reasoning, simple enough. So as k increases, k squared minus 1. The bigger the k, the bigger k squared minus 1. Squared minus 1 increases. Now, if the bottom getting bigger, the whole thing getting smaller. So the bottom getting bigger, the top, the whole thing will getting smaller. So this one decreases. So usually we use that. I would prefer to use that instead of using the derivative because that's a lot easier to do. So check. So both of these are satisfying alternating series tests say that this is convergence. There's another way to do this. Another way to do this is we're going to put the absolute values into it and we show that it is absolutely convergent. If it is absolutely convergent, then certainly it will be convergent. If it is convergent with the absolute values, it will be convergent without it. Right, once again, another way to do this is just put an absolute values into it. I'm going to put absolute values into it. absolute values will turn the negative 1 to the k power into 1. And we compare to 1 over k squared, which is a p series where p equal to 2. So that series, this series is convergent. So we say that one is convergent absolutely. So if it is convergent with the absolute values, it will be convergent without it. So this is another way to do that. But usually if we have negative 1 to power, that alternating series, don't have to do much. Right. Next example, we have this. Right. By the way, there is a reason why you say why most of the problem we have is in terms of a quotient. Have you wondered about that? Right. Because if I ask you what is the series of something like this, like factorial, then obviously it will be divergent, because factorial does not go to 0, right? So divergent test, if the k terms does not go to 0, then that's it. We will not say and nothing further. That is divergent, right? So usually this will be written in terms of a quotient. So e to negative k, if we move it down, we have k e to the k. Right. Now, one term on the top, one term at the bottom. Most likely ratio test. Because if it's more than one term on the top, more than one term at the bottom, we have to use the limit comparison test. But on this one, we use the ratio test. Right. Before we do that, let's check the ranking. Which one faster? K is the power. E to the k is exponential. So we have the bigger term at the bottom, the faster term at the bottom. That means this one go to 0. Furthermore, not only it go to 0, when that is the case, this one is convergent. So faster term at the bottom, convergent compared to the ranking here. Right. So one term at the top, one term at the bottom, use ratio test. Because one term on the top, one term on the bottom. Usually that is the case. Right. Usually the case. Of course, unless we have something to the, or we can use the root test. If this one, let's say, raised to the k power like that, then obviously that is the root test. But we don't have that problem here. Need to find the eraser. We don't have that here. So ratio test. What is ratio test? For ratio test, we need to know let a of k equal to the term. So let a of k equal to k over e to the k. Now the ratio test, limit as k go to infinity. So the difference between the limit comparison test and the ratio test is that in the ratio test we compare the same terms in the sequence, consecutive terms in the sequence, where comparison test we compare the two sequences together, so a of k over b of k. This is, both of them come from the same series, consecutive terms of the series. So we have ace of k plus 1. We're going to put k plus 1 top and bottom there for k. And then divide by ace of k, the same thing. Divide fraction is multiply reciprocal. Now, k plus 1, k cannot really do that, but e to the k and equal k plus 1. This one we can break it down into e to the k times e. By the way, since all of these are positive, we don't need the absolute values. Yeah, just no need absolute values. Just use the bracket. And that term will be written as e to the k times e to the first, e to the k over k. So the top we just have k plus 1. Yeah, like I said, no need for absolute values. The bottom e to the k, e to the first, which is e times k. Now, when we're trying to find the limit, take the one with the highest power on the top, the one with the highest power at the bottom. By that I mean ignoring the 1, ignore the plus 1. We have k over e to the k, e times k, sorry. K and k cancel out, we have 1 over e. Now, let's write it out. So we have limit of ace of k plus 1 over ace of k as k goes to infinity equal to 1 over e. E is 2.7 something, 1 over e is going to be less than 1. By ratio test, if less than 1, it will be convergent, absolutely. So absolutely convergent. So meaning it will convergent without the absolute values. So that series is convergent. So in that case, just use the ratio test because of the type of problem. Right. By the way, if we use the divergent test in this case, it will be inconclusive, because if we take the limit of that goes to infinity, the faster term at the bottom, so this one goes to 0. If the k term goes to 0, the test is inconclusive. Divergent test is inconclusive. So we use the ratio test on this one. Right. Next we have this problem and this problem. Both of this we will use limit comparison test, simply because more than one term at the bottom. This one also limit comparison test, but with a twist. So this one, because of that, alternating series test. So when we look at the problem, most likely we kind of see the form of the problem, so we have some idea what we should use. All right, limit comparison test. Why? Because more than one term at the bottom or the top. Right. So use limit comparison test. because we have more than one term from the bottom or the top. Right. Now, what do we compare to? Right. We will compare to the term that where we just keep the fastest term or the biggest term on the top and then the biggest term at the bottom. So what we compare to is, so compare to, by the way, I have to make one change here. If 0 put in here, 5 to the 0 power is 1, 1 minus 1 is 0. We cannot have that. So please change this to 1. Otherwise, it is undefined. We don't want that. But like we mentioned this before, whether we start from 1, 2, 3 or 0 doesn't matter. Missing the first few terms does not change the convergence or divergence of the series. So adding the first few terms or remove the first few terms, the series is still convergent or divergent. Nothing will change. The values will change, but in terms of convergent or divergent, nothing will change. So what we actually compare to is just this, ignoring the 1, because 1 is significantly less than 5 to the k. So we compare to this, which we'll put all together into 3 and 5 to the k, because both of them have power of k. So what do we see here? What kind of series is this? Well, if you say it's a geometric series, then you are correct. As mentioned before, usually that when we use the limit comparison test, we compare to the P series or the geometric series. So in this case, we compare to the geometric series, and that one geometric series where r equal to 3/5, which is less than 1. And absolute values are less than 1, it will be convergent. So that's all we have. Oh, sorry. Now the actual solution. Right. So using limit comparison test. As most of this one we use that limit comparison test. Right. First, for comparison test, we have to have a of k and b of k. So let's just write that out. For the series, let a of k be that. And now we compare to this. Where b of k is 3 to the k, 5 to the k. Right. Limit comparison test, we have to take the limit of the ratio as k goes to infinity. Right. So a of k, b of k. multiply reciprocal. Right. Next, this -1 is negligible, so we just ignore it. So we just have that, and we will cancel out, and we have 1. So cancel that, and this is equal to 1. Now, limit comparison test. If we check the ratio and that is between 0 and infinity, it is convergence. So the limit and we did say that if it is equal to a constant between 0 and infinity, that means they have comparable rates, so behavior will be the same. And since b of k is convergent, so is a of k. So, right. So 1, which is between 0 and infinity. By the way, this one, even if it is equal to 0, it's still fine. If it is equal to 0, meaning that the bottom is a lot bigger than the top. Right? Now, if this is equal to 0, the bottom is bigger than the top. But the bottom is convergent already. B of k is convergent. A of k even less than convergent. Certainly will be convergent. Right. But in this case, it's equal to 1, which is that. So we say the series behave the same. Even spell it. And since the sequence, the series bk converges, because this is a geometric series with the ratio between -1 and 1. Now they behave the same, and one of them is convergent, the other one is convergent as well. I said most when we have more than one term, limit comparison test will be useful. There's some twist into that. There might be some twist. So make sure that, remember, the comparison test, the term have to be positive. The cosine here, some of them might be negative. So that's why there's a little twist on that problem. And then in this problem as well. If we start at 1, put 1 in here, 1 square minus 3, that one's negative. If we put 2 in there, it will be positive. So even though the first term is negative, where we put 1 in here for k, that's okay. Just ignore the first term. Like I said, missing the first few terms, the series is still convergent or divergent. Nothing will change about convergent or divergence if we remove the first few terms. Right. I will still need to write that note. At k equal to 1, k squared minus 3, over k squared plus k minus 1 is negative. And the limit comparison test, that's what we use here. Limit comparison test only used for when the term is positive. Series with positive term. Right. That's what we need to be mindful of. So in that case, don't worry about that. Either we're going to put infinity into it, put absolute values into it, or we're just going to consider for k greater than or equal to 2. In this case, we just ignore the first term. Still work just fine. The case when k greater than or equal to 2. Because when k equal to 2, 2 squared is 4 minus 3 is positive. So everything greater than 2 will work. We have to worry about that. So limit comparison test still work. But for k greater than or equal to 2. Right. So limit comparison test. Right. Like I said, now we will go from 2, so we don't have to worry about the positive don't have to worry about the negative term. We'll compare to just that highest power term on the top, highest power term at the bottom, or the highest ranking term on the top, highest ranking term on the bottom, and then that cancels out just 1 over k. That's what we let b to the k equal to. And then of course we still need to show that the limit equal to a number between 0 and infinity. I didn't say that the limit comparison test is easy. I say that it is easy to use, but it's not the most direct solution. Right, so we do that, check the ratio. Right. H of k, that. B of k. Multiply reciprocal. Multiply into it. We have k cubed minus 3k over k cubed plus k minus 1. and highest power term on the top, highest power term at the bottom. And that is equal to 1. Now, if it is equal to 1, the ratio, then they have compatible rates, behave the same, and one of them convergent, the other one convergent. But in this case, b of k, this is harmonic series, that one divergence. But this is equal to 1, so they behave the same. Because if it is between 0 and infinity, they will have compatible rate. So behave the same. And we have the series b of k. This one is divergent. Because this is a p series, p equal to 1, or it is a harmonic series. Harmonic series is divergent. So they behave the same, and b of k is divergent, so a of k is divergent. This will be from 2, right? Is divergent. Now if divergence starting from 2, it will be divergent starting from 1 as well. So we have to make some minor adjustment, but after all, it's still a limit comparison test. The next one is still limit comparison test as well. Right, this one also limit comparison test because we have more than one term. However, need to make some adjustment because cosine of k potentially be negative. Limit comparison test only works if it is positive, if the terms are positive. Right, so in that case, let me just write that note again. Limit comparison test. Work for positive terms only. Right. So in this problem, we will consider the case where we just put absolute values into it. Right. So we consider the series here. So we want to put absolute values into it. Just make sure it will be positive. This is not going to be equal to 0, right? Because cosine equal to 0 is only when we have pi over 2 or 3 pi over 2 or adding a pi to it, right? Now, for those values pi over 2, 3 pi over 2, those are irrational number, right? So those k values for irrational number, pi over 2, 3 pi over 2, those will give us 0. But the k here are integers, right? Or whole numbers. If you put 0, 1, 2, 3, 4, it doesn't have pi over 2 into it. It will not equal to 0. So that's why we don't have 0 either. We only have positive. By the way, k to the 3 half plus 5, k 0, 1, 2, 3, 4. So this is going to be positive. We only need the absolute values on the top. Now, what do we compare to? First of all, the cosine k, where we have absolute values, it will be less than 1, right? Because cosine is the wave between -1 and 1. So cosine, absolute values of cosine is less than 1. Right. In this case, we can compare to, just consider 1 on the top. So we use 1 on the top instead of that. And the highest power at the bottom, we use 3 half. We don't need the 5 because the 5 is significantly less than k to the 3 half. Right. And the limit comparison test still the same. So this is b sub k. And for that one, we will let a sub k take the limit. A sub k that divide fraction is multiply reciprocal. This is not the best option for sure. Multiply reciprocal. And we ignore the 5. Yeah. That's negligible, so we just ignore that. K to the 3 half is a lot bigger than that. Cancel out, just have cosine of k. Ouch. Still the limit though. Right. What we have here is cosine of k doesn't matter what it is. It will be less than 1, which is less than infinity. So meaning that they have comparable rate. By the way, I mentioned that it is equal to a finite constant, but in fact it doesn't have to be a constant. As long as it is between 0 and infinity, they have comparable rate. They behave the same, and the rest. and then we have b sub k. This one is convergent because p series, p is 3/2 greater than 1. Right, they behave the same, so a sub k is convergent as well. Is there another way to do that though? This sounds like a bit complicated. Right. So let's look at this. We start with cosine of k, absolute values less than 1, right? Now, we can divide by k to the 3/2 on both sides. Why? Because k to the 3/2 will be positive when k greater than or equal to 0. Now, the elegant, oh, by the way, let's make it equal to so it's proper. Yes. It's not going to be equal to because k take the integer values. It cannot be equal to 1 either. Wait. Now, of course, cosine of 0 is equal to 1. Yes, it still can equal to 0. It still can equal to 1. But only the first one. After that, cosine of pi is -1, cosine of 2 pi is 0. We're not going to have 2 pi if we put integers numbers here. So except for the first one, when k equal to 0, it is equal to 0. This is the only value for k where cosine of k equal to 0. Right, so it's still fine, less than or equal to, no big deal. So cosine of k less than or equal to 1, cosine of k divided by that less than or equal to 1. Now my question is, can I just add 5 here at the bottom? And the answer is yes. Why is that? Because the bigger the bottom, the smaller the quotient. So actually, no, it doesn't work. If this is a -5, then yes. If this problem is something like -1, it will work, and we use the direct comparison test because of the first 5, so we have to use the limit comparison test, so it doesn't help. If it is -1, then we can just say like that, smaller the bottom, bigger the quotient. Yeah, and we say this one is convergent, anything less than that is convergent. So this is the direct comparison test, but we cannot do that because of the first 5. We cannot write it is less than, because when +5 we have something smaller than it, so it doesn't work. So this is what we have to stick with. Right, next one. What do we use? Obviously, when we see this -1, that is the alternating series test, and we don't need to worry much about anything else. Alternating series. So we need to write what is the term, what is a sub k. As mentioned before, k -1, k +1, k doesn't matter. As long as it changing odd, even, alternating between even and odd, we're good. I will just take out the term negative 1 raised to k minus 1, and this is h of k. So in the alternating series, the term without the negative 1 to the k minus 1, you consider the term of the alternating series. And alternating series test, we check two things. First is the limit equals to 0. So we just take the limit here. Right. And then of course we put infinity in finite over infinity equal to 0, right? Yeah, so check finite over infinity. So yes, that's good. Second is h of k non-increasing. And answer is yes, because the bottom getting bigger, the quotient getting smaller. We don't even need to take derivative. So we say as k increases, square root of k is increases, square root of k plus 1 is increases, is increasing. So h of k equal to 1 over square root of k plus 1 decreases, because bigger the bottom, smaller the quotient. The quotient getting smaller. So yes, decreases is non-increasing, so which is good. So both of them are checked by alternating series test. That is convergent. Converges, always said it is convergent. Either way, works. Right, we have that. Right. Now next one is a little different than what we doing so far. We have two terms. Now this one, obvious, kind of an obvious. What we see is a telescoping series. Something a little less obvious if we see something like this. Oh, sorry, k plus 1. Something like that where we can do partial fraction. Sometimes we have to use a partial fraction. I'm not even sure about that. I'm sure about this one though. Yeah, so this one is the telescoping series where we do the partial fraction. So this one, we don't have to do partial fraction. Right. So it's the telescoping series because they have two terms, one positive, one negative. And so this is special. Right, so the telescoping series, just put a bunch of numbers in and see what happens. When k equal to 1, 3, but 3, put 1 in here. Right. And then next, Let's put 2 in it. Just keep doing that. And let's just keep going. Keep going. Let's say if we put n into it, what happened? And we call this is the partial sum. So rather than go to indefinitely to infinity, we stop at n. So we'll put n into it. Right. Now let's simplify this and get a better sense of what this actually is. 3 minus 2 is 1, so we have 3 over 1 minus 3 over 4. Right. We don't even need the parentheses here, right? That's fine, just give it. And then 3 times 2, 6 minus 2, so 3 over 4. And then 3 over 7. Next one, 3 over 7. 3 over 10. All the way to 3 over 3n minus 2 minus 3 over 3n plus 1. Now, I'm using the color code to make it easier to see. So the term is positive. I'm going to write in differently. So 3 over 1 minus 3 over 4, 3 over 4, 3 over 7, 3 over 7, 3 over 10. I don't know what in the middle here, but 3 over 3n minus 2 minus 3 over 3n plus 1. When we learn about scoring series, we actually use the dominoes, kind of help us to visualize this. Right. So now we see that cancel with this, that cancel with this, and this will cancel with the next one, and essentially it will cancel with this one too. So think about this. Each term has a plus and a minus. Everything cancel out. We left with one plus sign from the beginning, from the first term. If we left with one first positive, at the end we have to have one more term that is negative, right? Because every time we cancel, a positive and a negative cancel out. Since we have one positive term remains on the top, on the first term, we need one negative term remain on the last term. So that is equal to this. So we say S of n equal to 3 minus 3 over 3n plus 1. So that is the partial sum. Now if we want the whole thing, the whole series, it will be equal to the limit of S of n as n go to infinity. So just take this limit go to infinity, and that will be easy. And we have this many times 0 over, I mean finite over infinity, so this one go to 0 because finite divided by infinity. So this one equal to 3. So actually this sum, when we add up, it is equal to 3. So if it add up equal to a constant, this is convergent. In this particular case, we even find out that it is equal to 3. Right. Right. Next, we're going to do this. Now this one obvious because of the power of k. So I say obvious a lot, but in this case it is when we have the power of k. This is the root test. Right. So for the root test, actually let's just write out what is h of k. H of k equal to the whole thing with the power of k. And the root test, we will take the limit. Let rho limit as k go to infinity. The root of h of k. Throw an absolute value to guarantee that it is positive. In this one we don't really need that though. K is from 1 to infinity, so k is positive. So certainly k plus 1 over 2k is positive. So just divide them. Right. Power on top, index of radical at the bottom, or just 1, right? So if we have 2k here, then we have 2k over k, which is fine. So that's why I write like this. In this case, just 1, or just cancel out. Because it is positive, right? K is positive, k plus 1 over 2k is positive. So that's why absolute values is not needed. K over k is 1, so we just have k plus 1 over 2k. Now as k goes to infinity, only the one with the highest power terms matter. So k over 2k equal to 1/2. And this is less than 1. So by the ratio test, if rho is less than 1, the series is convergent. By ratio test, rho equal to 1/2, which is less than 1. The series is convergent. Right. So we have quite a few examples in this section. So, like I said, This might come in handy if we can see right away the k terms does not go to 0. But if k term go to 0, move on for the other test. Need to know the ranking though. And most of this example we see that it is comparison test, limit comparison test. And limit comparison test, it is only for positive terms. If something like that, have to throw in absolute values. For something like that, we can ignore the first few terms, so it's still positive. If we just have a term on the top, a term at the bottom, that's the ratio test. When we have -1 ratio some power, alternating series test. And on the special case, we have the alternating series as well. The root test, where we have the power. Right. It helps if we do a lot of examples. I don't think even this is enough, but I think I have to stop the video here. So with that, we finished chapter 10 about sequence and series. Thank you for watching, and see you in another video in Calculus 2.